Hello, everyone, and welcome to another AP Chemistry virtual lesson. My name is Michael Fairbaugh, and I teach AP Chemistry at Albemarle High School in Charlottesville, Virginia. The topic of today's lesson, we are still in Unit 7, but this will be the end of Unit 7, so we'll talk about solubility equilibria today. I just want to remind you that if you haven't visited apstudents.org/exams2020, that is a good website to check out information about taking AP exams. And specifically, the AP Chemistry exam, the date on May 14th, you can see that there are a variety of different times. So depending on where you live, that's the time at which you'll be taking the AP Chemistry exam. So again, more information coming from the College Board about the specifics, but you can tell for chemistry, there'll be 2 free response questions. And again, there's a lot more information on the apstudents.org/exams2020. Hopefully you have access to a periodic table and some scratch paper and something to write with. In today's lesson, we will wrap up Unit 7, and we're focusing on solubility equilibria. And so in today's lesson, I will talk about solubility and Ksp, which is the solubility product, the equilibrium constant. We'll talk about the common ion effect and how solubility is related to pH, as well as how can we use a comparison of Q versus K for Ksp to predict if a precipitate will form. Our warm-up problem is the AP problem that I had assigned for homework from yesterday's class. So we have a equilibrium situation, which you can tell up at the top here. We can see the double arrows. So this is our equilibrium system, and we have calcium carbonate. When heated, decomposes according to the equation shown above. In a study of the decomposition of calcium carbonate, a student added a 50-gram sample of powdered calcium carbonate, CaCO3, to a 1-liter rigid container. The student sealed the container, pumped out all of the gases, and then heated the container in an oven at 1100 Kelvin. So the total pressure that we're looking at is the pressure of the CO2 that's being formed. And it looks like right about here, somewhere between 10 and 15 minutes, that would be when equilibrium has been achieved. Because at that point, the pressure, not the concentration, because we're measuring pressure here, but the amount of CO2 did not continue to increase, but rather level off and remain constant over time. So for this particular reaction, the decomposition of calcium carbonate, we have CaCO3 on the left, and then calcium oxide, CaO, and carbon dioxide on the right. So part A of this question, calculate the number of moles of CO2 present in the container after 20 minutes of heating. So we'll go back to our given information. So we have a volume, we have a temperature. Now we have this number here, which is grams, but it would be a mistake to convert this from grams to moles because we have to go with the data. And the data indicates that we have a pressure of 1.04 atmospheres. So if equilibrium has been achieved, then it's possible that not all of this 50-gram sample was actually converted completely into CO2. And in fact, in a second trial, they used 100 grams of calcium carbonate, but they got the same final pressure. Again, that 1.04 atmospheres, which is going to be the pressure of the CO2 as it leveled off. So if I've got a pressure and a volume and a temperature, then I'm going to calculate moles by using the ideal gas law. So we have rearranging this equation, N equals PV over RT. So on the equations and constant sheet, you can find the value of R, the ideal gas constant, which if we use atmospheres would be 0.08206. They gave us a pressure of 1.04 atmospheres in this problem. We have a 1-liter container and 1100 Kelvin. So we're all set up to calculate the number of moles of CO2 in the container. So I'm going to go ahead and round this off to 2 significant figures based on the 1100 for the temperature. So I'll call this 0.012 moles of CO2. Okay, so that was part A, to calculate the number of moles using the ideal gas law. On to part B. Now the student claimed that the reason why the final pressure in the container became constant is because all of the calcium carbonate had decomposed. Well, I'm pretty set up to disagree with this claim, but let's talk about what's going on here. Okay, so we had initially 50 grams. Now you could look on the periodic table and you could find the molar mass of calcium carbonate. So calcium is about 40, carbon's about 12, and oxygen 16. So we have about 100.09 if you use all of the decimal places for the atomic masses for these elements. And then of course, there is only 1 mole based on the balanced chemical equation. 1 mole of CO2 for every 1 mole of calcium carbonate. Now, notice that in part A, we had 0.012 moles of carbon dioxide, and that was after the pressure had leveled off for several minutes. So this is a good reason to disagree with this claim, because if all of the calcium carbonate had decomposed, then the reaction would have gone to completion, and you would have produced 0.5 moles of CO2. So I disagree with the claim because we only have 0.012 moles of carbon dioxide in the container. Therefore, if all of the calcium carbonate had decomposed, as the student had claimed, then the number of moles of CO2 would have been higher. This suggests that, in fact, equilibrium was achieved, and that's why only some, but not all, of the calcium carbonate was converted into CO2. Another way you could have disagreed with this claim is based on the fact that in trial 1, they used 50 grams. And in trial 2, they used 100 grams, and yet they got the same final amount, the same final pressure. So if all of the calcium carbonate had decomposed, then we would have expected twice the amount of CO2 if we used twice the amount of calcium carbonate. But since we got the same pressure in both experiments, that suggests that the calcium carbonate is not being used up completely. So here are the official scoring guidelines. Again, there are 2 explanations. One, you can actually calculate the number of moles of carbon dioxide that would have been produced if the reaction had gone to completion, and compare that with the actual amount from part A and say, no, that's less. Or you could have said that doubling the amount of the reactant did not lead to a double in the amount of product. Therefore, this reaction did not go to completion, and there must have been an equilibrium achieved. All right, part C of this question says, after 20 minutes, some CO2 was injected into the container. So this reminds you, hopefully, of the comment that I made yesterday about, see if I can spell his name right. So Le Chatelier's principle, okay? And Le Chatelier's principle has to do with what happens when we make a change. So if we somehow add more CO2 to this equilibrium, that should cause Q to become larger than K, and then a shift in the equilibrium position that would go toward the left. So it says after 20 minutes, some CO2 was injected, raising the pressure to 1.5 atmospheres. Would the final pressure in the container, assuming it would have reestablished equilibrium, would it be less than, greater than, or equal to 1.04 atmospheres? So we got 1.04 atmospheres in 2 different trials using 2 different amounts of calcium carbonate. So it seems like the equilibrium pressure should still be 1.04 atmospheres. Assuming that temperature remains constant, equilibrium was reached in both experiments. Therefore, the equilibrium pressure of CO2 at this temperature should be 1.04 atmospheres. Now, after the addition of additional CO2 raising the pressure to 1.5, then there would be a shift toward the left, toward the reactants, and equilibrium would be reestablished with a final pressure of exactly 1.04 atmospheres again. All right, on to part D of this question. Do we have sufficient data from the information in this question to answer the value? What is the value of Kp? Now, normally an equilibrium constant is products over reactants. So take a moment and look at what I've written here. I've got products, so calcium oxide and carbon dioxide over calcium carbonate. Do you see anything wrong with my Kp expression? Well, if you look closely at the phases of matter and just kind of use common sense here, you're not going to have the pressure for a solid. In fact, we never, in a heterogeneous equilibrium involving different phases, we never include pure liquids or pure solids in the equilibrium expression. So our Kp is reduced to one term. And we already know that the pressure of the CO2 in each of these trials is 1.04. So yes, there are sufficient data to determine the value of Kp. All we really needed was that one measurement of 1.04, and that was obtained in both experiments. So we now have our value of Kp. All right, I gave you another AP practice problem. And I like this question a lot because there's something that students will do, and I'm going to show you kind of the wrong way to do it and the right way to do it. But there's something that students will do with a equilibrium problem. So what I think should jump out at you when you look at this question is right here. And I'm going to call your attention to something that was mentioned earlier in our discussion of equilibrium. And this is in topic 7. Specifically, topic 7.5 in the AP Chemistry course and exam description, the magnitude of the equilibrium constant. So some equilibrium reactions have very large values of K and then proceed essentially to completion. Other equilibrium reactions have very small values of K and barely proceed at all. So you may recall in an earlier lesson talking about acids and bases, and you can find information on the AP equations and constant sheet about what's called the Kw. This K is extremely small, so 10 to the negative 14. So the predominant form in a sample of pure water is water molecules. So pure water does not conduct electricity. Now a student might think, well, wait a minute, aren't these ions present in solution? Not very much. If the fact that K is extremely small tells us that water is mostly just water molecules and very, very, very small amounts of these ions, pure water does not conduct electricity. Now on the other side, if I flip that equation around and put H3O plus, which is the sign of a strong acid, the hydronium ion, and then the hydroxide ion, which is the sign of a strong base, if I reverse a reaction, then you have the inverse of K. Well, what's the inverse of 10 to the negative 14? 10 to the positive 14. That reaction essentially goes to completion. Look at the large magnitude of that K. So when you have a strong acid and a strong base, they completely neutralize each other. So going back to this large value of K, this is going to show up in our discussion. So pay attention to that large magnitude that's coming up. Okay. And it even says this in the stem of the question in part A, considering the value of K for the reaction, determine the concentration of the product. In this case, we're talking about this chemical formula Ba, that's barium, and then this ion, this polyatomic ion, which is abbreviated EDTA. So what's the concentration of this in 100 mils of solution? Let's go ahead and focus on the information that was given to us in the problem. We have 50 milliliters of a solution that contains EDTA at a concentration of 0.3 moles per liter. We have 50 milliliters of a solution that contains barium nitrate, and we're kind of focusing on the barium ions here and not the nitrate ions. So 50 plus 50 is 100. What is the concentration of the barium EDTA complex ion in 100 milliliters of the solution? I'm going to do some mole calculations to get started. I'm going to figure out the moles of barium. So volume times molarity equals moles, as long as I can get my units to cancel out. So I've written 1,000 milliliters on the bottom instead of 1 liter, but they mean the same thing. So when I cross off the units, I get moles of barium nitrate, which is the same as moles of barium. So do this math. We get 0.05 times 0.2 and 0.01 moles of barium. I can do a similar calculation, volume times molarity for the other solution, which had a concentration of 0.3 moles per liter. So I've got moles of barium and moles of EDTA. Now here I'm going to go down the wrong path just to show you what some students did in solving this question on the AP exam. So what they did was they set up a rice table. So again, we are ignoring the large magnitude of K for the moment and doing a traditional rice table. I already calculated the moles of barium and the moles of EDTA. I'm going to go ahead and just keep this rice table in terms of moles as opposed to changing to concentration. Now the barium has to go down by a certain amount, X. EDTA has to go down by a certain amount, X. And again, that's a 1-to-1 mole ratio. So therefore the product has to go up by X. All right, so what students did is they set up the equilibrium expression. Now, if you're good at math, then you are going to follow me perfectly on this next slide. If you're struggling with math, you might find this is a little bit challenging. But what I'm trying to say in terms of the message is that this is not the required way to solve this. I'm actually showing you the wrong way to do it because I want to kind of take this wrong path, follow it to completion, and then we'll talk about why that was unnecessary. So we're going to go ahead and just do the math. Multiply both sides by the denominator. Looks like I have to FOIL because I've got two expressions there. So 0.01 minus X, 0.015 minus X multiplied. Okay, now I have to distribute that big number, that 7.7 times 10 to the 7. Oh my goodness. You may recall that I said in yesterday's lesson that the AP chemistry exam is not going to require you to use the quadratic equation. I went ahead and did a quadratic solver with my A, B, and C from this ugly equation. And when I solve for X, this is what I got. Essentially, I got 0.01. So the message here is that you did not have to do that math. The value of K is very large. And as was mentioned in the course and exam description, you can assume that reactions with a rather large, I would say, around 1,000 or higher value of K essentially goes to completion. So therefore, if X is equal to 0.01, essentially, this is a limiting reactant problem. You're going to run out of barium before you run out of EDTA because 0.01 is less than 0.015. So the reaction essentially goes to completion, producing 0.01 moles of the product. Okay, so barium is the limiting reactant. And so there's a 1-to-1 mole ratio between reactant and product. So the limiting reactant determines how much you produce. Now, the answer to this question, which we haven't gotten yet, is what is the concentration of barium, EDTA complex, the product, in solution? And it was 100 milliliters or 0.1 liters. So our answer, 0.01 divided by 0.1, is 0.1. Now, watch how simple the official scoring guidelines look on this question. So it says, based on the K value, the reaction goes essentially to completion, and barium 2+ is the limiting reactant. So when you go from 50 plus 50 to 100, you're essentially doubling the volume. And when you double the volume of a chemical, you cut the concentration in half. So 0.2 becomes 0.1. And so effectively, if the concentration of barium ions in solution is 0.1, then the concentration of the product, the barium EDTA complex ion, is also 0.1. So that was a much easier way to solve that question. But again, many students ignored the large magnitude of K and tried to use a rice table. Whether they were successful or not, that was kind of a waste of time. Okay, there was another part of this question which will get us back to Le Chatelier's principle. Remember that in Le Chatelier's principle, a system that is at equilibrium experiences an external stress and then will respond to that stress. Now, what is the stress? They added water. So by adding water, they went from 100 milliliters of solution to 1,000 milliliters of solution. So each concentration the barium, the EDTA, and the complex ion has been diluted by a factor of 10, going from 100 to 1,000. So here's our K expression, but now we have Q. And each of those concentrations has been diluted, reduced by a factor of 10. Well, there's a 1/10 on the top and on the bottom, so that will sort of divide out, cross out, but I still have an extra 1/10 on the bottom, which when I flip that, because it's on the bottom, it becomes 10. So effectively, my Q is equal to 10 times the value of K. So what did the dilution do? The dilution with water causes the concentration of each substance to decrease. And then as a result, Q becomes larger than K. And when Q becomes larger than K, equilibrium will shift in this direction. So the question is asking, after this equilibrium has been reestablished, is the number of moles of barium greater than, less than, or equal to the number of moles of barium that was present before the dilution? But because we are shifting as a result of Q becoming greater than K, we're shifting toward the reactants, toward the left, then the barium will be greater. Now I'm going to make a comparison to another example of Le Chatelier's principle, and that is gases. Here we have 2 moles of gas on the left and 1 mole of gas on the right. So a different number of moles of gas on each side. Suppose that we take our container, which contains these gases at equilibrium, and we increase the volume of the container. As a result, the pressure will go down, and the system will shift toward the side of the equation with the greater number of moles of gas as a way of counteracting this decrease in pressure. Well, there's a completely analogous system with aqueous species. While these aren't gases, by adding water, we've effectively increased the volume of the solution, and we caused not the pressure, but the concentration of each of these species to go down. So instead of shifting to the side which has a greater number of moles of gas, we're still going to shift to the side of the equation that has a greater number of moles of aqueous particles to counteract this decrease in concentration. So it's completely analogous to the situation that happens with gases. All right, so your official scoring guidelines say that the number of moles of barium increases, and you could have said because when you dilute a solution, that's going to increase the percent dissociation of the substance, in this case, shifting toward the left. But another way to justify this is a Q versus K. It's a great argument that you can plug in those numbers, the 1/10 dilution, prove mathematically that Q becomes larger than K, and that will produce more reactants as equilibrium is reestablished. All right, so we're going to talk today about solubility and Ksp. What you're looking at right now is a substance that is not very soluble in water. Now, I didn't say insoluble, I said not very. So we have to make a distinction between insoluble and very slightly soluble to talk about Ksp. Suppose we have a beaker of pure water and a sample of solid is added to the beaker. The solution is stirred for several minutes, and then the solution is left undisturbed for several minutes. And now the solution looks like this. Now, some might classify that there's a white solid on the bottom of the beaker, indicating that this solid did not dissolve at all. Let's look a little closer and see what is actually happening at the particle level. Is this solid dissolving? Well, here we're looking at a close-up view of the crystal lattice. So these are all of the ions here. So this is the solid. And as you can see that we have some aqueous ions surrounded by water molecules. So we're getting both dissolution and we're also getting precipitation or crystallization is happening. So both the dissolution and the precipitation are happening at the same rate. That sounds a lot like equilibrium. So you're going to have a solid that is dissolving, but maybe not very much. So are you suggesting that the value of K for these types of solids is large or small? So think about that. Think about the value of K. Now we're going to have barium sulfate, which breaks up into barium and sulfate. Magnesium hydroxide, which because there is a subscript 2 outside the hydroxide, breaks up into 2 hydroxide ions along with 1 magnesium. Notice I'm putting the charge on the ions. Calcium fluoride breaks up into 1 calcium ion and 2 fluoride ions. And silver carbonate breaks up into 2 silver ions and 1 carbonate ion. Now, if I were to write, let's say, barium sulfate and write the K, and again, not paying attention to phases of matter, I might think that it's going to be concentration of barium times the concentration of sulfate divided by the concentration of barium sulfate. But if I pay close attention to the phase of matter here, remember, pure solids and pure liquids are not included in equilibrium expressions. You can't have the molarity of a solid, or again, a pure liquid. We're going to call this Ksp, where Sp stands for solubility product. So there is no denominator in these expressions. Now there is a coefficient of 2. I'm going to write an exponent. So I have that little superscript there. So these are the Ksp, the equilibrium constants, the solubility product constant for these solids. Now, is K rather large or small? Well, let's go ahead and look at some examples. I've got silver chloride, silver bromide, and silver iodide. Take a look at the magnitude of those Ksp values. Okay, it's very small, indicating that these are practically insoluble. I say practically because they are slightly soluble. Now, solubility is not listed in this table because we are going to calculate that. But suppose you didn't have a calculator and this question were asked. Which substance, silver chloride, silver bromide, or silver iodide, has the greatest solubility? If you didn't have a calculator and all you had was the Ksp values, well, I would assume that the larger the Ksp value, the larger the solubility would be. And that is a good assumption to make based on this comparison of very similar compounds with similar formulas. They have a 1-to-1 ratio between cations and anions. So I would assume that silver chloride is the most soluble without doing any math. Now, how would you do that math? Because again, solubility and Ksp are related to each other, but they are not the same thing. So please don't say that the solubility of silver chloride is 1.8 times 10 to the negative 10, because that's not true. All right, well, I've written the expression for silver chloride dissociating into silver ions and chloride ions, and I've written the Ksp expression. What I'm going to do is recognize there's a 1-to-1 mole ratio between the silver chloride itself and the silver ion. So the concentration of silver or chloride, I could use either one, is the same as the solubility. So if I can figure out the number of moles per liter for silver, then that is the solubility of the entire compound in terms of moles per liter. So how do I do that? I'm going to go ahead and write the Ksp expression. I know what the value is. It was given to me in the table. And I'm going to call each of these concentrations, because they are the same, it's a 1-to-1 mole ratio, X. I mean, you could call it S for solubility. Some textbooks do that. I'm just going to go ahead and call this X. And when I solve for X, I'm essentially just taking the square root of the Ksp. And when I do that math, I get 1.3 times 10 to the minus 5, and that's moles per liter. That is the solubility of silver chloride in water at that particular temperature. And it's usually a standard temperature of 25 degrees Celsius or 298 Kelvin. If I take the square root of the silver bromide Ksp, I'm going to get a smaller value. If I take the square root of the silver iodide Ksp, I'm going to get a smaller value. So without doing any math, I could have predicted which one was the highest solubility. But if I had to actually calculate it, it was a simple square root of the Ksp. So again, the concentration of the silver happened to be the same as the solubility of the entire compound. Here's a different chloride. This is not silver chloride, but lead chloride. Notice that the formula of lead is not PbCl, but rather PbCl2. So we have a slightly different Ksp expression with the exponent chloride squared. So which ion, in your opinion, the lead or the chloride, would have the same value as the solubility of the entire lead chloride compound? Hopefully you can recognize we are looking for a 1-to-1 mole ratio between the formula of the solid and the ion. So it's going to be the lead, not the chlorine, that would tell us the concentration is going to be the solubility. There's a slightly different way of solving this problem, and that's because we cannot say it's X and X. For every 1 mole of lead that is produced in this dissolution, you get twice as much. For the concentration of chloride, it has to be twice as much. So now when I plug X and 2X into my Ksp expression, and by the way, the Ksp for lead chloride happens to be 1.7 times 10 to the negative 5, I am not going to simply take the square root of 1.7 times 10 to the negative 5 because the math works out a little bit differently. So while we have to take the concentration of chloride and square it according to the equilibrium expression, inside the brackets represents the concentration. And again, it's not X and X, but rather X and 2X. Some students struggle with this because they say, why are you doubling it and squaring it? The doubling it has to do with moles and mole ratio and stoichiometry, but the squaring, that's a separate event which is related to kinetics and rate laws and the equilibrium constant expression. Those are two separate things, and they are not being done at the same time, and therefore we should somehow cancel one and only do one and not the other. These are two separate things that both are required for this expression to be true. So what goes inside the brackets is X and 2X, but when you do 2X quantity squared, that's 4X squared times X, this is what you get. Now, if I want to solve for X, which is going to be the concentration of lead and therefore the solubility of this compound, I have to take the Ksp, divide by 4, and then take the cube root of that. So when I do that, I get 0.016, which represents the concentration of lead as well as the solubility of the lead chloride. So what's the concentration of the chloride ion in this saturated solution of lead chloride? It should be twice as much, so it should be 0.032. So for a saturated solution of lead chloride, we have these concentrations, and the solubility of the lead chloride would be the 0.016 because that's the 1-to-1 mole ratio between the formula and the lead. Now, I'm going to ask you a question. This is a little bit different than the silver chloride, silver bromide, silver iodide comparison I gave you earlier. And here's the question. Which of these two substances has the greater solubility? Now, it's not really fair for a teacher to ask a trick question, but this is completely a trick question, and here's why. We had in the earlier comparison, silver chloride, silver bromide, and silver iodide. They were all a 1-to-1 ratio between the cation and the anion. Here we have manganese and carbonate, and we have manganese and hydroxide. So that's a 1-to-2 comparison versus a 1-to-1 comparison. So that's not a good or fair comparison. Therefore, this is potentially a trick question. So I'm going to go ahead and solve, and this might surprise you and kind of confirm why it's a trick question, because you might think that the higher the Ksp, therefore this would lead to a higher solubility for the manganese carbonate. But again, we're going to have to deal with an x squared versus a 4x cubed. So we're going to get a different solution here. When I take the square root of the Ksp for manganese carbonate, I get 4.8 times 10 to the negative 6. But I am not doing a simple square root for the Ksp of manganese hydroxide. In fact, I have to do what I did before for the lead chloride. Because of the x and the 2x and the 4x cubed that I get, I have to take the Ksp, divide by 4, and take the cube root. So look at that. it turns out that the solubility of the manganese hydroxide is actually greater. So this would not be an easy question to answer without doing the math. Therefore, I think that the important point I want to make is pay attention to how you set up your KSP problems. All right, moving along to another situation where we can calculate. I have barium sulfate and magnesium hydroxide. We're going to calculate the molarity and also the grams per liter. So if you have your periodic table handy, it might be a good idea to calculate the molar mass of both barium sulfate, BaSO4, and magnesium hydroxide, Mg parentheses OH2, because you'll need a molar mass to go from moles to grams. All right, so I have my barium sulfate, X and X, 1-to-1 mole ratio. Square root of the Ksp gives me 1 times 10 to the negative 5. That's my solubility in terms of moles per liter. Now, how do I take that 1 times 10 to the negative 5 and convert that into grams? Well, as I said, you have to calculate the molar mass of barium sulfate. And if we do that, the moles cancel out, and I now have grams per liter. Again, this is not insoluble, but slightly soluble. So about 2.3 milligrams of barium sulfate per liter at room temperature. All right, we'll do a similar calculation for the magnesium hydroxide. Again, watch out for how you set this up because it's not going to be a simple square root. It's going to be that 4x cubed that I talked about. It's a 1-to-2 mole ratio. So we end up with 1.1 times 10 to the negative 4 for our solubility. That is the concentration of magnesium, and that is the solubility of the magnesium hydroxide. I'm just going to go ahead and add parentheses. Oops. Forgot my formula, didn't have parentheses on that. All right, let's take our 1.1 times 10 to the negative 4 and convert that into grams per liter. So the molar mass of magnesium hydroxide as determined by looking at the periodic table. And now again, we're just confirming how small that solubility is. So about 6.4 milligrams of magnesium hydroxide for every 1 liter. If we've gone from Ksp to solubility, we should be able to go the other way around. So now I'm going to give you the solubility of 2 different compounds. This is calcium fluoride, CaF2, and silver carbonate, Ag2CO3. Can we go from grams per liter to Ksp? All right, let's again get our periodic table so we can figure out the molar mass of CaF2. So the molar mass of CaF2 is calculated, and this will take me from grams per liter to moles per liter. Now, does the 1.1 times 10 to the negative 3 moles per liter, does that refer to the concentration of the calcium ion? Or does that 1.1 times 10 to the negative 3 moles per liter, is that the concentration of the fluoride ion? Think about that. Hopefully you can see, based on the 1-to-1 mole ratio, that the concentration of calcium is in fact the solubility of the entire compound. So the concentration of fluoride is not 1.1, but rather 2.2 times 10 to the negative 3. If I plug in those values into the Ksp expression, I will get the value of Ksp. We're expecting a pretty small number here, and sure enough, Ksp for calcium fluoride works out to be 5.3 times 10 to the negative 9. All right, we'll do this again for the silver carbonate. We're going to start with grams, and again, we have to use the molar mass of silver carbonate. So the molar mass of silver carbonate allows us to go from grams to moles. Is this number that we get, 1.3 times 10 to the negative 4, is that the concentration of the silver or the concentration of the carbonate? So remember, you're looking for that 1-to-1 mole ratio between the compound itself and the aqueous ions. So that number, 1.3 times 10 to the negative 4, that is the concentration of the carbonate, which means that the concentration of silver should be not 1.3, but 2.6 times 10 to the negative 4. So plug in those values into the Ksp expression. Again, we're expecting a pretty small number for Ksp, and sure enough, 8.8 times 10 to the negative 12. So we have successfully done calculations using Ksp to go to solubility and solubility to go to Ksp. Hopefully you have a better understanding of those calculations. I now want to talk about a concept known as the common ion effect, and this has to do with Le Chatelier's principle. Now, the solubility of barium sulfate in pure water is 1.0 times 10 to the negative 5. So if I take barium sulfate and dissolve it in this solution, which already has some sulfate ions in it, then my question to you is, what is the molarity going to be? So if a sample of barium sulfate is dissolved in a solution that already contains 0.0015 molar sodium sulfate, do you predict that the solubility of barium sulfate in that solution on the right is going to be less than, greater than, or equal to 1.0 times 10 to the negative 5? So again, think about Le Chatelier's principle. If we already have this additional amount of sulfate ions, that is going to affect the equilibrium. So with additional sulfate added to the equilibrium, we are going to predict a shift from right to left. And therefore, if we shift toward the solid, that will decrease the solubility of the barium sulfate in a solution that already contains sulfate ions. So let me go ahead and define for you. The common ion effect essentially says the following: that the solubility of an ionic solid is going to be less, it's going to be reduced when it is dissolved in a solution that already contains a common ion, as in one of the ions present in the solid. So if there is already barium, or if there is already sulfate in a solution, and then we try to dissolve some barium sulfate in that solution, we should have a lower solubility than it would be in pure water. So to go ahead and do this, I'm going to write my Ksp expression, but I am not going to write X and X. What I'm going to do instead is put the concentration of sulfate that we already know, which is 0.015, into my Ksp expression. That's going to cause the barium to be much less than it would normally be if I was just doing X and X. So as you can see, comparing the solubility in pure water with the solubility in a solution that already contains a certain amount of sulfate, it is less. When there's already sulfate, that shifts the equilibrium toward the left, making it less soluble. All right, I'm going to go ahead and extend this to pH a little bit. So what I now have is a situation of 5 moles per liter, but now in a solution that already has sulfate ions, the concentration of the barium sulfate is less because of the shift according to Le Chatelier's principle. All right, so I have pH of 12.0. Now that is a rather high pH, indicating that we have some hydroxide ions. So if there's additional hydroxide ions coming from a solution, then what's going on here is a shift toward the left. Our prediction is that the magnesium hydroxide should be less soluble in a solution that already contains a certain amount of hydroxide ions in it. So we're going to compare the value we get in the flask on the right with the value we would have gotten in pure water. You may have forgotten pH, so I'll just remind you that pH plus POH equals 14. And since the pH is 12, the POH would be 2, because 14 minus 12 is 2. Now 10 to the minus 2 would be the concentration of hydroxide. So that's how you go from POH to concentration of hydroxide. And if I plug in 1 times 10 to the minus 2 into my Ksp expression, and I solve for the concentration of magnesium, again, we're going to see if it's going to be less than 1.1 times 10 to the negative 4, which is what it was in pure water. And sure enough, it is much less. So again, the common ion effect. The solubility of an ionic solid is reduced when it's dissolved in a solution that already contains a common ion. All right, so this is kind of related, solubility and pH. I have 2 acids, HCl and HF. Now, which one of these acids is strong and which one of these acids is weak? You may remember that HCl is on your list of 6 strong acids. That means that HF, which is not on your list of strong acids, is actually a weak acid. So therefore, the majority of the HF exist as molecules, not in the form of H plus and F minus ions. So now instead of making the solubility less, we're going to show you examples of making the solubility actually greater. So the solubility of calcium fluoride is actually greater in a solution of HCl than it is in pure water. So you don't see H plus or Cl minus in this equilibrium expression. So you might wonder, what effect would H plus and Cl minus have on this equilibrium? So if I have HCl, I've got a lot of H plus ions and Cl minus ions. Focus your attention on the fluoride for a moment. I mentioned that HF was a weak acid, and you can tell it's a weak acid because look at that value of Ka, it's rather small. What would happen if I reverse this equation? 1 over the Ka would be 1 divided by 6.8 times 10 to the negative 4, and look how large that K is. Remember how small Ks emphasize the formation of the reactants, whereas large Ks indicate the formation of the products. So any H plus ions that are present are going to react with F minus ions, essentially going to completion. And that's going to cause the concentration of F minus to decrease. Now, according to Le Chatelier's principle, when you remove a product, then the equilibrium will shift toward the right, and that makes calcium fluoride even more soluble in an acidic solution like HCl than it would be in pure water. So to summarize, for solubility and pH, something like calcium fluoride, this reaction between the fluoride ion, which acts as a weak base, and the H plus ions or the hydronium ions from the acid causes the fluoride concentration to go down. Solubility increases as the equilibrium shifts toward the right. Okay, here's another example. This is calcium fluoride. This is silver carbonate. It is observed that silver carbonate is more soluble in an acid solution like nitric acid than in pure water. So it's the carbonate. Okay, last time it was the fluoride. It's the carbonate that is reacting with H plus, producing initially carbonic acid, but that rapidly decomposes to give you water and CO2. This is like the classic, vinegar baking soda reaction to produce bubbles. Okay, so that is going to cause the carbonate to go down, shifting the equilibrium toward the right, making silver carbonate even more soluble in an acid than in pure water. Okay, how about magnesium hydroxide? You find this in milk of magnesia. It's kind of a chalky solution, but yet it actually dissolves even more in an acid solution than in pure water. So if you add acid to something that looks chalky like magnesium hydroxide, it actually becomes even more soluble. So it's this negative ion, in this case, the hydroxide, reacting with H plus to produce water. This causes the concentration of hydroxide to go down as it's reacting with the H plus ions. And when hydroxide decreases, we shift the equilibrium toward the right, making it more soluble. So with respect to solubility and pH, I'd like you to focus on the anion. So if the negative ion is hydroxide, fluoride, sulfide, carbonate, phosphate, these are all examples of bases, then what they will do is they will react with the H plus ions, and then that will cause the value of the concentration of that negative ion to decrease. The solubility will then shift toward the right. Because of the equilibrium shift, the ionic solid becomes even more soluble in an acid solution. All right, I want to talk about Q versus Ksp, and then I will get to your homework problem. All right, here we have two flasks that are mixed together, and the two chemicals that we're mixing together here are barium nitrate, which contains barium ions, and sodium fluoride, which contains fluoride ions. So are we going to make a solid precipitate? It depends. It depends on Q versus Ksp. We're going to predict if a precipitate will form. So when you combine 100 milliliters of barium nitrate with 100 milliliters of something else, that is a twofold dilution. So the final volume is now 200 milliliters. That's going to cause our barium concentration to be reduced by half. So now we have half of that number, which is 6 times 10 to the negative 4. Now for the sodium fluoride, we're also cutting that concentration in half. So our concentration of fluoride in this final solution is 1.6 times 10 to the negative 3. Well, now that we have our concentration of barium and fluorine in this final solution, we still don't know whether a precipitate would form or not. We have to do a Q versus K comparison. Let's plug in these values for the concentration of barium and fluoride into the Ksp expression and see what happens. Now, if the Q is greater than the Ksp, then we have exceeded the solubility, and we're definitely going to get a precipitate. If the Q is less than the Ksp, then we have not reached the saturation point yet, and no precipitate would form. So we have barium. Again, watch out for the fact that it's squared. Okay, so that's going to be barium times fluoride squared. We do that math, and we get a number, which is 1.5 times 10 to the negative 9. Now that is less than the Ksp, so therefore no precipitate forms. All right, another example. This is lead nitrate, obviously contains lead ions, mixing with potassium iodide. So are we going to form lead iodide? Same kind of calculations as before. We're going to go from 100 and 100 to 200. So we cut our concentration of each ion in half. So the lead is actually half of 4.8 times 10 to the negative 3. And then the iodide is also half of 6.4 times 10 to the negative 2. So we've done that math. Let's plug in these numbers for the concentration of lead and the concentration of iodide into the Ksp expression. That's lead times the iodide squared. And it looks like 2.5 times 10 to the negative 6 is our numerical answer, which is greater than the Ksp. So yes, a precipitate does form. Now, what if you have a solution that contains more than one ion? Here we have some silver and some lead. And we're given the Ksps for each one, and we're going to add a sample of sulfate, potassium sulfate. Will a precipitate occur? There's our Q for silver, and they told us that the concentration of silver was 0.2. So there's my concentration of silver. This was the number of moles, but it was actually a 1 liter container, so that is also the molarity. So that is our concentration of sulfate. All right, let's see if we get a value for Q. All right, we'll come back to that in a moment. Let's do the same for the lead. They gave us a concentration of lead, which is 0.001, and that's also, coincidentally, the amount of sulfate that we have per liter. All right, let's compare it to our Ksp. Well, for the silver sulfate, 4 times 10 to the negative 7 is less than the Ksp, so no precipitate forms. And for the other one, the 1 times 10 to the negative 6 is greater than the Ksp. So a precipitate of lead iodide would, I'm sorry, lead sulfate would form, but a precipitate of silver sulfate would not form. All right, well, thank you for hanging in there. We talked about solubility and Ksp and the common ion effect and the effect of pH on solubility, as well as Q versus Ksp. So here is your AP exam practice homework problem, which I will go over in tomorrow's lesson. So take a screenshot of that. There is part A with Roman numerals I, and III. And we also have parts B and C and all of the subparts there. All right, reminder to check out the link in the video description for helpful chemistry resources. Again, this has been Michael Fairbaugh from Albemarle High School in Charlottesville, Virginia. Tomorrow is the deadline. If you need mobile tools or connectivity or know someone who does, go to cb.org/tech. Let us know by tomorrow, Friday, April 24th. All right, thank you very much for watching. Have a good day.